Colleagues, we continue our school. Today, the third lecture of today is from Professor Bardossy of Stuttgart, University of Stuttgart. And he is a well-known expert in the area of hydrology and meteorology. He is professor in the Institute for Modeling Hydraulic and Environmental Systems in the Department of Hydrology and Geohydrology of University of Stuttgart. He is very well known for various projects, for a large number of publications, and defended PhD students. He recently told me that he had 47 PhD students defended under his supervision. Maybe this number is already higher. So Professor Bardossy, floor is yours. 45 minutes of lecture and 15 minutes of questions and answers.
Okay, thank you very much. Okay.
I'm sorry, Professor Bardossy, I would like to yes, to say that also this school is co-chaired by Professor Alexander Gelfand, corresponding member of the Russian Academy of Sciences, who is also, we together, both of us would like to thank you for finding time to give the lecture to this audience.
Thank you. Great, thank you very much for this nice introduction, and it's a great pleasure for me to have the opportunity to give this lecture. I cannot say that to be here because I'm here every day. And it's a strange feeling to give a presentation for people whom you do not see. But let's start. Yesterday, I changed my presentation once more. Namely, I took off all the equations. I thought this is more student-friendly, and but there are equations behind these things. But let's start from a relatively distant future and a distant topic. Oh, what happens to my, just one moment. Yes, so if you look, the next appearance of Halley's Comet is on the 28th of July, 2061. So that's far future. But what does it mean? It means that we have scientists who are doing a very accurate job. If you ask us when will be the next flood on the Danube or on the Volga River, which is unusual, so for example, bigger than 10-year return period, we have no answer. And it will occur most likely before the Halley Comet. So is it so that hydrologists are simply not intelligent enough to do a good job, or are there any other problems? And if you look a little bit, this is a picture which is slightly similar to what Remco showed, namely if we try to calculate how many raindrops are falling, we try to register them, we may be very surprised because we cannot count the raindrops because they are too many. I just took a little event for a catchment of 75 square kilometers just south of Stuttgart, and took a 12 millimeter precipitation in 1 hour. That's nothing unusual. This happens every year, even a few times. If we calculate the number of raindrops, what we can do from their size, we have 10 to the power 13 to 10 to the power 14 raindrops. This is a number which is extremely high. So even for economists and people in the finance industry, this would be a big number, and which also shows that we will never be able to follow the fate of each individual raindrop, which means our modeling has to aggregate somehow. We have to do the modeling not necessarily on the scale where the things are happening. And if you would put them together in a line, you would have these raindrops on a distance 10 times the moon and back. So very clear conclusion: we cannot model each raindrop. So we have to do something else. And the modeling of the water cycle is a very complicated matter. In general, mathematical modeling is a kind of translating some problems or observations into the language of mathematics. And we try to do this in a way that we limit our descriptions to certain processes, and in hydrology to certain geographical areas. We make assumptions on these processes. So we usually look for kind of equations, differential equations, or whatever. And we use observations, variables for these, and then we try to get answers. Now, the question could be here, is our hydrological modeling, the way we do the hydrological modeling is correct? For a long time, there were trends that we have to have a community model. A community model in the sense like what meteorology has. But there is a big difference between meteorological modeling and hydrological modeling. Namely, meteorological modeling is going on in the atmosphere where you do not have limits, and we do hydrological modelings on catchments where we assume that the boundary of the catchment is a no-flow boundary. Basically a no-flow boundary. That means we can cut out the catchments, but that also means that we can very specifically look at the processes on a particular catchment. This is good and bad. It is good because we are specific. It is bad because we lose the generalization possibility, or we partly lose it. Of course, there were some general models, but they have often problems. The advantage would be, of course, if we would have some kind of general large scale, or not necessarily large scale, but unified models. They would allow us to have a deeper insight into the model. We would have less confusion. We could do a better training, so all people would do the same kind of things. We could have a better regionalization, but we have a big disadvantage. The processes going on in different catchments have different importance. In some catchments, for example, snowmelt is the main process which is important. In other catchments, you don't have snow at all. So they have very different importance. They have very different spatial and temporal scales, even for different catchments. If we do individual modeling, we can capture the unique features and we can go into detail with these. And the advantage here is also that we can better reflect the data availability and the uncertainty for individual parts. We do not really know whether meteorological models are better for Siberia than for Holland. So in general, the uncertainty can be very specific, and this is done in hydrology with care for individual catchments. Okay, but just a small illustration. Here on the left-hand side, you see the Kokcha River in Afghanistan, and on the right-hand side, a flood in my home country in Hungary on the Tisza River. You can immediately see that the processes corresponding to these catchments are very, very different. Here you don't see any kind of vegetation. Here you see vegetation, but of course at the moment underwater. So very different catchments, very different processes. Let's concentrate always on these. Okay, so. But at the beginning, I told you that we have very high uncertainty. We are just not as good as the astronomist. So why are we are not able to tell the future the same way as they do? We have a lot of sources for that. First of all, we have incomplete model formulations, incomplete descriptions of processes. Then once we have selected a model, we still have the problem that we have to fill this model with parameters. And many of these parameters are just unknown. We do not know too much about soils in detail, etc. So we have a problem of uncertain parameterization, and we have a big problem, and this is where I will focus on, namely the uncertainty of the observations. We have in the observations, we have observations like, for example, soil properties. These are static variables usually. They are not really, because even the soil is changing, and unfortunately we have all kind of creatures, mice and worms who are changing the soil properties, but we generally assume that soil properties are more or less constant in time. And we have a much bigger problem with our dynamic variables, namely with the meteorological variables, and also to some extent with the discharge. These are things which we cannot really measure very accurately, and they contribute very much to the uncertainty. Okay, so that is about the setting, what I would like to discuss. We usually, or very often, we use models which have to be calibrated. That means we want to adjust the parameters so that our model is giving the right results. So the model should transform rainfall to discharge, at least for the past, so that the observed and the model discharge are similar. Additionally, we would like to have parameters which are reasonable. We all know that certain things are simply unreasonable, even if the model works better, but it works better because of the wrong reason. We usually do this calibration by objective function minimization. So we try to formulate an optimization problem, and then we look for the solution of this optimization problem. And as Keith Bevan very often and very clearly said, we have very often a non-uniqueness in these parameters, and the glue procedure is one of them which takes this into account. But most of our objective functions are somehow related to the squared error. That is a very, very old tradition. We try to minimize the squared error, so we don't care too much about the small errors, but we care a lot about the big errors. So the big errors are usually emphasized in these objective functions and in the calibration procedure. Now, what if the biggest errors are due to observation errors? What happens to our calibration? Do we try to correct errors of the observations with new errors introduced into the model? So let's have a little bit more emphasis on the observation errors and on the observation problem. Okay, so as I told you, precipitation uncertainty is one of the biggest contributors here. You have to know that precipitation is observed usually in a discrete way. We heard Remco Uhlenhütt's presentation, who showed many new and very effective ways to measure precipitation. If we would just look at the gauges, we measure discretely in space and time, and we have a very small total area. We have in Germany about 1,000 online precipitation gauges, which means it's about 20 square meters. 20 square meters for the whole territory of Germany. So it's a very small area, and that means we have a very big problem. Another big problem what we have is that we cannot capture the aerial extremes really well, because we have only discrete observations, and in general we have a problem where we can see with some previous studies, we showed that in about 2/3 of the cases we are underestimating extremes, and in about 1/3 of the cases we are overestimating them. So we have very frequently wrong estimations. And of course, if we measure in our network rainfall, one thing what we can be sure about, that at a given time when we measure at our stations, there was a point in the area where the precipitation was higher than all these points. This is absolutely sure. So once we then try to calibrate our model, we do the parameter estimation and this smears. This tries to compensate for precipitation bias, tries to compensate for individual errors, and in general, it tries to reduce the large errors. Due to the unmeasured extremes, very often we have here a substantial problem. Okay, so with this, we are at the research question, which I wanted to discuss with you, or at least to present to you. That means if we have a hydrological model, is there a realistic realization of precipitation so that the model performs well? So is there something, what could have been the rainfall, but we just did not measure it correctly, and then suddenly the model would do a good job? So we are not looking at the model parameters, we are not looking at the processes, but we are looking at possible realistic precipitation. What is a realistic precipitation? It is a lot of constraints what we can put here. First of all, we look for precipitation which does not contradict precipitation measurements. What does it mean? It means that we look for kind of realizations of precipitation now in space and time, which puts values to the measurement locations which are equal to the measurements, which only changes values in between the measurements, which also reproduces the spatial variability of the observation. So we are not inventing new structures of rainfall. It has to be something which really looks like rain. and which also follows the distribution of the observed values in between. So practically, if we observe precipitation values between 2 and 5 millimeters, then we should not invent somewhere in the area a new precipitation value of 100 millimeters. So we should remain always in the domain, or should not differ very much of the domain of precipitation values, what we measured at the observation locations. So if a precipitation field fulfills all these conditions, then it is a realistic realization of precipitation. Okay, so that's at the moment the definition. And now we look, do we find such realistic realizations of precipitation such that after it the model performs well? So do we find something which looks like rain, looks like the rain on the given time, and gives a good model performance? This is a very very complex problem. Of course, it depends on where and for what you want to apply it. We kind of change or calibrate now precipitation. It would be better maybe to call it inverse modeling. So we have a space-time problem, which can be very high dimensional. The last example, which I will show you, has more than 100 million unknowns, 100 million pixels in space and time, with very, very many constraints, all the precipitation observations, the spatial structure, etc., which in our case is about 500,000 constraints. So that also means that if all these constraints are fulfilled, we assume that our fields look like rain. Okay, so that is what we are looking for. And what we will do is we will somehow take an excursion in these fields. This is a huge space of possible fields, and we will go continuously through this domain of fields, and we will always look, okay, is this better? Is this not better? So it will be an interesting excursion. Okay, so the first example for this excursion is a historical flood. The biggest flood in the Upper Neckar was in 1882, a Christmas event on the 24th and 25th of December. There was a very high extreme at Tübingen. Of course, we can ask, was this a realistic precipitation event? So is this something where we just did wrong measurements? Can we model this? And can we understand the process, what led to this flood? Okay, so it's a historical question. It's politically neutral, so we can speak about it. Okay, so what did we do? We selected a historical model, the historical model, or the hydrological model for this historical flood. The hydrological model is the well-known, very simple HVV model, which is where we used it in a spatially distributed manner. What we did is that we said, okay, one of our big problems in the past was that we did not have enough observations. So we calibrate the model on recent observations, so on the recent time period. And then we try to use this calibrated model for this past event and try to have a look how this performs. We collected all possible precipitation observations for 1882. which are in and around the catchment. Relatively few of them. And we use the model which has a daily resolution. Okay, so this was the setting. And here you see the simulations for the present. And on the upper panel, you see the rainfall. And in the in-between panel, you see the snow accumulation, and here the melt, and then accumulation melt. And here below, you see in red the observed discharge, and in blue the simulated discharge. It works very nicely, and we could also model the snow accumulation and snow melt reasonably well. This is important for this 1882 event because there was cold weather before Christmas, and snow melt certainly contributed substantially to that flood. Okay, so now we have a model. Now we have something where we believe this is a good representation of the rainfall runoff process. And now we move on and we look how would this model work if we use interpolated precipitation for this event. We use the whole year 1882, but here you only see November till December, because this is the important part. Red is the observed. You see the peak is somewhere above 900 cubic meters per second, and the gray line, what you cannot see very well maybe, but it's not bad. You don't see it very well because it's very bad. The peak is around 400 cubic meters per second. So if we just take the variables as they are, it just does not work. It is a serious problem. And if you look here, this is the catchment. This is the catchment of the Neckar to Tübingen. And the red points are the points where we had historical precipitation observations. Here you see the scale, and this is in meters. So we have quite a few observations, but most of them are around and outside the catchment, and only 2 of them are on the boundary. So the precipitation uncertainty in this catchment is very, very likely to be very high. So what do? We try to generate fields which fulfill these conditions for the realistic precipitations. So first, we for every single day we collect the data and look at the distribution of these data. Here you see the empirical distribution for a given day as a red line, and then we fit a distribution to this. We allow only 10% higher precipitation to occur in between. This is not a very unusual assumption. If you look, we used the very dense network, and we looked how often do we have precipitation in the stations which were not in the historical and which were above the maximum, and more than 10% above the maximum which was measured at the historical locations. And we had 86% were more than 10% above it. So we can imagine that there is 10% more precipitation, at least at one location, than what was maximally measured. Okay, but we do not allow other values, and we exactly want to have only these values and exactly this distribution. So we are not putting more high precipitation into the domain or low precipitation, but we use this domain. We fill this domain with a precipitation field. Okay, and then what do? We try to model then always the discharge. So we are concentrating on the last 2 months. We use a warm-up period of 10 months. We are concentrating on these 2 months and not only on the single event, because we do not think that a model which only fits one event well is in generally also good. We want to see whether this works in general reasonably well. We select days with relevant precipitation in this time period of November and December, where we concentrate on. Those were 24 days. 24 days with relevant precipitation. We will change these with a so-called conditional simulation method, where the conditions are on the observed values. So they have to match the observed values everywhere. The variogram, which is a typical seasonal variogram, and the discharge, the observed discharge. And this is the unusual part. We want to have precipitation fields which give us the reasonable discharge. The method what we used is a so-called random mixing with a so-called Whittaker-Shannon interpolation, and we generate in total 100 realizations. You can look up this if you're interested. I deliberately threw out all the equations because I once heard that every equation is causing about half of the listeners to fall asleep, and then this would be a bad thing for me. So we use that, and we will not produce one single realization. We will produce 100 realizations, but we could produce thousands of realizations which work reasonably well. And let's look, these are the realizations what we got, for example, for the 24th of December 1882. These are only 2 out of the 100 realizations. In the upper panel, we see 2 precipitation fields. Here you see the precipitation amounts are scaled to 0 to 100, but we do not have those high values here. These are the 2 most different ones. Okay, so they can, the 2 fields can differ quite a bit, and these are the 2 most similar ones. But even the most similar ones have differences. So all these 100 precipitation fields are different. They are different, and then we'll look at a different day. Here we see, for example, for the 25th, we see very different precipitation, but this does not contradict our observations. And these 2 are the most similar ones. Even these differ to some extent. So we can get a large number of possible explanations, and this is a reasonable way to look at this. And let's see, what do we get? We have, for all the 100 realizations in 1882, we have an S-subscript value of 0.92 or larger. And you see the red is again the observed, and the gray is the simulated rainfall, which looked like rain and fulfilled all the conditions. And you see we could match everything very nicely, and compared to the Neckar, what we had before with minus 0.27, these are worlds. This is very, very different. Okay, so that is what we got. If we would go the traditional kind of uncertainty way, we would use glue. We would generate a lot of different model parameters. And here you see what the different, the large number of model parameters would give. They are way out. They certainly, the parameters cannot explain the differences between observed and simulated. So this means we have to take the observation uncertainty also into account. And if we combine the two, we combine the different model parameters with the different precipitation realizations, then we get a very, very nice, very good covering of our observed discharge curve. So this means that for this particular case, there were precipitation fields which look like rain, which fulfill the conditions that they have exactly the observed values, which do not invent high extra precipitation, but are able to describe the discharge. Okay, here, this kind of precipitation, what we simulated, is something where very similar rain also occurred in the recent 20 years. So this kind of precipitation is not unusual from its spatial pattern. Okay, so, and if with this we can generate scenarios. Here you see two scenarios with the maximum snow and the minimum snow, and you see the precipitation on the individual days. They are different, but they are all very good for the discharge. So there are many possible rainfall fields which do not contradict observations and produce a good discharge. Okay, from this we could also answer the question, what was the contribution of snowmelt? And depending on which scenario we'll look at, we have values between 13 and 23%. That's good to know, because this means that even with less snow, we could have had a big flood, but also with a high snowmelt could have contributed to this flood event. Okay, so now I come to somewhat shorter description of a little bit more complex cases. On the Tyne and in the Neckar River, we use there two different models: the sheet run, which is a more or less physically based, and the HPV, what we did before, and we had long time periods. And here you see for the Tyne how these modifications are done. You see we are gradually changing the rainfall and always going into the hydrological model and looking at how the hydrological model is working. This is for the Tyne catchment. The specific thing with the Tyne and this Neckar example is that now we have much less freedom because we have a lot of observations. But still, with these lot of observations, we can have big differences. Here you see the orange line is the interpolated, the discharge simulated with the interpolated precipitation. Blue is the observed discharge, and the colored ones here in between are the simulated ones. And you can see the interpolation led to an underestimation here, but the simulation enabled us to describe this very accurately. And here you see some fields. In the middle you see for a given day the interpolated precipitation field, and these 8 are just randomly selected 8 realizations for that given day. They are all very, very similar to the observations, of course, to the interpolation, but they have much more variability both in space and a little and to some extent also in the distribution, because interpolation always smears the distribution. Okay, so variability seems to be very, very important for the discharge production, and this is what we capture here. Here you see for the Neckar an example. Again, orange was the interpolated, blue is the measured, and here I show this case because here the measured was below the interpolated. So this was the rare case where we have a kind of overestimation of the extremes. So, but we have a very clear improvement. And the other thing is, we do not really have improvement, or we do not necessarily have a big improvement in the low flows, because that's a different process. Another realization, again, you see the high similarity of the rainfall fields, but the corresponding discharge is much better if we use any of these. Okay, again, an example where here the interpolated is the orange dashed line, and we could improve. I have lots of such examples. I could show you for each realization and each day, and spend all the rest of this year just showing you figures and numbers. And now you can also see that the improvement of the model is substantial. We had originally an S-Sutcliffe, for example, for the ends of 0.77, which went up to 0.89, which means we have less than half of the squared error after this procedure. So this does not mean that we found the right rainfall. This also only means that the rainfall could be responsible for 50% of the variability. What we also looked is whether we can transfer data from one to the other, or we can calibrate simultaneously. So we did a lot of interesting, funny games with this. But I think my time is nearly over, so I have to come to the discussions. So what did we assume? In this case, we assumed a temporal independence. We assumed that the rainfall of one day is more or less independent of another day. This is reasonable for daily. There you have very low serial correlation, but especially in the spatial pattern, but this would be not the case in hourly. There we need space-time simulations. This is, again, a little bit more difficult to think. The other thing is we had to look at how long is the memory of a catchment, because if we change the daily precipitation on a given day, it will have an effect over a certain number of days, and each catchment has a kind of memory when it after which it forgets. So when we change the precipitation, it does not show too much effect after that time. So of course, the question is now, should we use the discharge for precipitation estimation, not only the precipitation for discharge estimation? And the other thing is that we have global data sets. We have global data sets of precipitation, discharge, and evapotranspiration, but it's always someone else who does it. And if you look at the water balance, it is completely violated. In most of the cases, it just does not fit together. I think we should focus very much on bringing these things together so that they are also in a physical balance, so that we have global data sets which are hydrologically reasonable. The presented procedure is complex. I don't want you to repeat this. You may do it. It's a nice exercise, but it's quite a bit of work. But what we could learn from it is that not only the models are uncertain, but also the data are very uncertain. And errors can be, to a large extent, be explained by precipitation uncertainty. Usually more than 40%, even for the dense recent network. The problem of uncertainty in our observations, precipitation observations, is much larger for data sparse regions. Like in the historical case, it's much easier to find an explanation. And my conclusion, personal conclusion, is that we should not only focus on the models and the model parameters. An acceptable model for me is a model which, using a realistic precipitation, in the sense how I defined it, functions well. And my final conclusion is do not try to correct data errors by changing model parameters. And with this, I'm at the end. Thank you for your attention. And I have to acknowledge two of my colleagues, Faizan Anwar and Jochen Seidel, who contributed to different examples, and their names should be mentioned. Thank you for your attention.
Professor Bardossy, thank you very much for a very interesting lecture. So we move now to questions. It would be good if you maybe could click yes. Okay, so we can see you. Right. So questions. First question is from Vsevolod Moredo, and it reads as follows. If we can infer precipitation distribution only from the observation points, how do we know the properties outside or between these points are realistic? Should we use perhaps leave one out approach?
Oh yeah, of course we could try to assess the uncertainty of the precipitation distribution alone with some kind of leave one out approach, but I try to do this a little bit more with the help of dense networks. So if you have like in the historical case a sparse network, and you have for the same region also a dense network, with that you can assess to some extent the uncertainty of the distribution.
Right, okay, thank you very much. Another question comes from Dr. Pelagia Belyakova. Question reads as follows. There are some attempts to provide global river discharge reanalysis using the least flood hydrological model together with the ERA 5 reanalysis. What is your opinion on such idea?
Oh God, it's difficult to answer, because my opinion is that ERA is highly biased in some regions, and if you adjust highly biased things to other highly biased things, I'm not sure whether you will be always successful. So I'm very, very skeptical.
Right. Okay, thank you. Next question comes from Nikolai Yasinsky. Professor Bardossy, are your methods on slide 20 used for precipitation simulation common for snow distribution, snow melt, and rain? If they could differ, so how would they?
Snow melt uses also an additional variable, namely temperature. And we could also simulate spatial distributions of temperature. In this case, this was not that important. But of course, you could use that also.
Thank you very much. Another question from Nikolai Yashinsky. Can we use these methods with downscaling the reanalysis data, for example? Is it the same as for gauges?
Yes and no. You could use it for downscaling. In fact, we tried something with that, but then your constraints become different. Your constraints are integrals on a higher scale. This can be taken into account, but I never really went far enough with that.
Thank you. Another question comes from Julius Peterson Barsena. Question is this. What software would you recommend to generate the rainfall realizations?
I cannot recommend anything really. We did everything ourselves, so it's our own development. Parts of this development are also available publicly, but of course the codes are not very well documented. But if you are interested, you can write me an email, and I'll try to get you some of the software.
Thank you. Question from France, from Mark Ehrlich. You mentioned two mechanistic distributed hydrological models. How the effects of grid size influence the obtained simulation results?
This is a very different question, because we treated this problem of the spatial resolution in a different context. In this case, we kind of deliberately decided that we take a 1 kilometer resolution. It would be, if you use interpolated precipitation, then from the precipitation viewpoint, even 1 kilometer is an overkill, because your interpolated precipitation is much smoother. You do not gain too much with that. But with simulated precipitation, you can gain. And the importance of this thing is also that you include this uncertainty, this variability, because in my opinion, hydrology is not only driven by means. Hydrology is to a large extent driven by variability.
Thank you very much, Professor Bardossy. We may have some minutes to maybe invite listeners, actually lecturers of this school who are now present in Zoom, to ask questions if they want. Professor Eilenhut, Professor Gelfand, Professor Kotsoyanis.
Can I take advantage of my position and ask one more question? Professor, what is your opinion? Should we use discharge for precipitation estimation?
Yes. In my opinion, at different parts of the world, we could do that. We were working on a case in Guyana where we had relatively few observations, but relatively good scaling possibilities with discharge. But of course, in that case, it was seasonal or monthly precipitation. Where of course, in this special case, evapotranspiration was not varying too much, and you could correct the absolutely unreasonable precipitation values, some of them reasonably well.
Okay, thank you.
Other colleagues, any questions? Yes,
I have a
Professor
question.
Eilenhut.
Thank you very much, Professor Solomatine. Professor Bardossy, thank you very much for your inspiring presentation. A question I have concerns observation errors and uncertainties in the discharge measurements. So to what extent would they affect this type of analysis? You're putting emphasis on errors and uncertainties in the precipitation measurements, which are certainly there. I confirm that. But what about, let's say, the downstream discharge observation errors?
Okay, thanks. Thanks very much. That's a very good question, because I threw that out of my presentation, and now I can give my opinion on that. The discharge uncertainty is a little bit different, because especially at locations where you have relatively stable cross sections, there you can say that your error is different because it is relatively stable in time. So practically the error when I measured the same water level is likely to be the same. While for precipitation, if I measured on one day and on the other day, the error is totally independent. So practically, what I tried to do is to take a kind of uncertainty of the rating curve into account, where we assume that the rating curve is stable, but we do not know it. We do not know it exactly. Of course, you could have the problem where you have lots of sediments and changing beds. Then you have to structure that. That means you can take time periods between big floods where you assume that there is, for that time it is stable, and then you can do lots of work with rank correlations, which is fun.
Thank you very much.
Colleagues, so I see yet another question came to the YouTube channel. So from Maria Ivkovic, question is this: how the errors in different methods of rating curves creation affect the problems in hydrological modeling?
I just answered partly this question. It was
yes.
Professor Uhlein's question. So practically, it's a very essential problem to find under which conditions or under which time periods the rating curve did not change, even if we do not know it. But at least we know what was bigger and what was smaller, and that's a very, very useful information.
Right. Okay, so we came to an end of this session. Colleagues, I would like to thank you. Unless Professor Kotsoyanis has a question.
Yes, just a short one. Thank you, Andras, for the excellent presentation. I wonder the reason why you highlighted the last point, which I agree with. Don't change the parameters. I guess you have some negative experience. Could you explain us, tell a few more words about this experience?
Thank you. This is in fact one point what hurts, because if you look, if you just do something what people relatively seldom do, that you do a little bit of water balancing in shorter time periods, you may see that you have a flood where there was just not enough rainfall before that observed. And what we do then is we try to modify certain parameters to get closer to that flood, and with that we completely destroy the validity of the model. And of course, one possible approach would be to be careful and cut these things out and not to try to calibrate on that. But I must say, personally, I don't know anyone doing that.
Right, exactly. So we don't calibrate to bad data. By the way, there was a nice paper in Journal of Hydroinformatics by Jean Kunsch. It was maybe in 2000 something, which is called On Data and Models. So maybe it would be interesting to look at it. Colleagues, again, Professor Bardossy, thank you very much for interesting presentation. I would like also to thank all other lecturers. So we're clapping hands here. To thank all other lecturers of today and even of yesterday. So we will continue tomorrow. Please check the schedule. So tomorrow we will start at 17:15 later, Moscow time. So it's 16:15 Central European Summer Time. Why? Because second speaker, Professor John Pomeroy, who starts at 6:30, who is in Canada. So we would like to give him some hours of sleep and not to force him to wake up at 5 o'clock in the morning. So that's why we start tomorrow a bit later with a lecture of Professor Ross Woods, and then Professor John Pomeroy would give his presentation. So please check the presentations which are uploaded on the website. Again, thank you very much. And on behalf also of Professor Gelfand, I would like to thank also our funding agency, Russian Science Foundation, which kindly provides funding for hydrological and modeling research in Russia. Very nice. And again, thank you and bye-bye.
Thank you very much. Thank you. Bye.